Okay, welcome in. In this video, we're going to talk about recursion, which truthfully is something that I don't use personally a ton, but I think it's a very cool topic in programming, computer science in general. It's doable in R, and I think it's something that's very elegant and interesting. So it's something that's worth talking about, even if for me it's not the most useful thing. So to start, I've defined a function here that calculates the factorial of an integer or I think this will just work for integers. I actually haven't thought about it for non-integers, but you're probably familiar with factorial of 4, say as 4 times 3 times 2 times 1, which equals 24. In math, we'll usually see 4 with an exclamation point, but that syntax doesn't work in R. There's actually a predefined R function for factorial, which I will show here. You can see it's a function. It actually uses the gamma function, which gamma of x is x minus 1 factorial. So this is just gamma of x plus 1, but that I digress. That's a separate topic. But there's a preloaded function for this. But let's say we wanted to define our own for whatever reason. We wanted to adjust it. Again, we have capital FUN to show its function. Factorial, we take an input or an argument x. The way I do this is I just start with some result. I set it equal to 1. And then from 1 to x, we loop over from 1 to x, and each time multiply the result by the number. So if x is 3, we would get result is result times 1, because that's, the first value of x is 1, then times 2, then times 3, keeping track the whole time. And we return our result, which becomes our factorial. And, just to make sure this works, we can define our function, and then we can run this on factorial of 5. And I happen to know the factorial of 5 is 120, but let's just show you. It comes out to 120. So this works, and it's fine, and it's all good. And it's pretty fast as well. I think if I do system time, which allows you to see like how long code is taking. If I do it on fun factorial 5, I don't know why I paused, but I get essentially 0 time. So very, very speedy function, even though we have a for loop. It'd be harder if I did like fun factorial of 150 or something. So anyways, let's say I want to do this instead of with looping, kind of this awkward looping thing. Let's say if I want to do this by recursion. Okay. And recursion is a funny joke is like, what's the definition of recursion? Well, it's recursion. Or on Google, if you say, if you type recursion, it'll say, did you mean recursion? And you click on recursion, it'll go back to the same page. So basically kind of means you're turning the function in on itself and going deeper and deeper and until you reach some value. And the key, the way we're going to start, which is also the way that recursion ends, is we're going to start with a break condition. Which will tell us to actually get out of this like loop that we're creating. It's not really a loop. So we're going to say if x is equal to 1, then we are going to return, I need my curly braces. Oh, that's not a curly brace. Embarrassing. Get rid of the square brace. And if x equals 1, we are going to return 1. So that's going to be our break condition. And that's going to make more sense in a second. And the only other piece we need in this function is we're going to return x times fun factorial x minus 1. So this looks a little bit weird. We are calling the function fun factorial within fun factorial. And just, to make things clear, oh gosh. Okay, I'm just gonna, oh my goodness, sorry, I can't type today. Okay, we are gonna remove the function fun factorial. It's not predefined. It's not something that's in memory. It's not like we're using a previous version. We're calling the function within the function that we're defining it as, which sounds tautological. It doesn't sound like it makes sense. Like we're using a word to define the same word. But this is a pretty cool, and first I'm just going to show you it works, and then we're going to talk about why it works. Geez, I cannot type. So I define the function. I now have the function defined, and if I call it on 5, I'm going to get 120. So pretty cool that this works, and it's a little bit weird, but let's walk through exactly what happens. So basically, let's say that like x equals 3. Let's say we're doing fun. I'm just going to do fun for short, fun of 3. We're going to go through the code, and first, if x equals 1, we return 1. X does not equal 1, so we go on to the next part of the code. We're going to return x, which is 3, times fun factorial of x minus 1, which is fun factorial of 2. So fun 2. And now we have this kind of object. Well, we have 3, which is a constant, but we have fun factorial of 2, which means we have to evaluate this function for 2. So we go back into the loop. or go back into the function. If x equals 1, it does not equal 1. So we go on to the next piece of code, return x, which is 2, times fun factorial of x minus 1, which is fun factorial of 1. So we still have the 3 from before times now this x, which is 2, times the fun factorial of x minus 1, which is fun factorial of 1. And now, we have two constants. We have a function of a number, so we just have to calculate the function. Here we go through, we see does x equal 1. In this case, x does equal 1, so we just return 1. And since we return 1, the function is over. We don't go to the rest of the rest of this code. So we get 3 times 2 times 1. And look at that. That's the definition of a factorial. We get 3 times 2 times 1, which is 6. If we run fun factorial on 3, we're going to get 6. So pretty crazy how that works. And you can imagine, obviously, I just did it for a simple example, but you can imagine if it's like 100, it's going to do the same thing. Basically, it's kind of like deriving something and the terms keep coming down and the x term keeps getting smaller. You get the value and then you run the function again on itself on a smaller number all the way until you get down to 1. So I think it's pretty elegant. One issue is that it's not super fast. For example, let's try fun factorial of 100 and let's do system time. System time. That's actually pretty solid. Let's try 1,000. So we get, this is the time for our function. And now let's try ours default function. So you can see ours default factorial function is way, way faster than our function. So, in this case, it's not like a super fast solution, but we're also just doing it on a funny example where we already have a predefined function for it. So there are times when, this might be the fastest or the most elegant or most useful way to write something. So definitely keep that in mind. And the other important thing is it's really important we have this break condition, kind of like a while loop that, just has true as the condition. This thing will run forever if we don't have a break condition. Like let's just comment the break condition out. We redefine this. And now if I run fun factorial of 5, it's going to say, no, too much stack usage. You got a huge number too close to the limit. Basically, this is saying this function ran forever. It kept doing x times fun factorial of x minus 1. And since there was no break condition, this kept going until x was like super, super negative times. These terms just kept collecting, like, we basically it continued in this way and got all the way down to, fun of negative to 10 million or something. And we got too close to limit. So the break condition is really important because otherwise we're stuck in a loop forever. But I think this is really cool. It's something that, it seems a little bit more like, it's more like art than something, like hardcore programming or following rules. It's pretty interesting that you can define a function within a function, and pretty interesting that a function can operate on itself without even, before it's even really defined. So I think recursion is really cool, and hopefully you do as well. Hopefully you find better uses for it than I have, but if not, we'll see you in the next video.